In this section, we're going to go further with the idea of association between quantitative variables. So we're going to do what's called a regression analysis and get a regression line. Y is going to be the response variable, the dependent variable, and when we graph it, it's going to be the vertical axis. X is going to be the independent variable, the explanatory variable, and it's going to be the horizontal axis when we graph it. So we're going to use this to do predictions. And if we let y hat, over here on the left-hand side in the middle, denote the predicted value of y, we write an equation, y hat equal a plus bx, or you might see it written y equal bx plus a. You might even see something like y hat equal mx plus b. So a is the y-intercept and b is the slope of the straight line. Let's take this example. Here's the regression equation that's been given to us. Y hat equals 61.4 plus 2.4x. If you have a femur, a thigh bone, you know how long it is, you can predict the height of the person that it came from. Y hat is the height. So if you put in 50 for the length of the femur, you get the height of the person is 181.4 centimeters. The y-intercept is the predicted value for y when x is equal to 0. But if this is actually a situation like we have here, a thigh bone cannot be 0 length. That makes no sense. But it does help us to plot the line. So you should be aware of that. The slope says how much does y hat change when x changes by 1 unit. And they give a nice example here saying the femur change of 1 centimeter gives you a 2.4 centimeter increase in predicted height. How about if we look at our slope values? Suppose this is a regression line, one of these three, for what happens when you have more years of education. Does your annual income tend to go up, go down, or stay the same? Now when we do this, we're going to have predictions, but we're going to have mistakes. It's not a perfect thing. So if we calculate for each observation what we really got versus what we had predicted, so that what we really got is the y, and y hat's what we had predicted, and we subtract, we see what the change between those is. That's called a residual. So a lot of times we're looking at the positive value of the residual. So if it's negative, we just change it by using absolute value. The closer it is to the actual one, the closer the predicted one is, the better the prediction, of course. So if we take all these residuals and square them and add them up, we have the residual sum of squares. Now, if we situate our line to where we minimize that sum, that's called the least squares. And that's what the computer programs will do for you. The regression line has some positive residuals and some negative, and the sum and mean of the residuals is equal to 0. It goes through the point x bar, y bar. So it goes through the average for the explanatory variable and the average for the response variable. If you look at the slope, you can actually memorize this formula. The slope is equal to r times s sub y over s sub x, where s sub y is the sample variance for the y variable. And s sub x is the sample variance, or sorry, I should be saying standard deviation. The variance is s squared. So s sub x is the standard deviation for the x variable. And you can actually calculate the y-intercept by taking the average for y, subtracting from it b minus b times the average value for the x's. Correlation describes the strength between them. It doesn't change if your units change. For instance, if you looked at two people and you measured them in centimeters or you measured them in inches, if one was twice as tall as another, it doesn't matter what units of measure you use. So that's how correlation works also. The units do not affect the strength. And it doesn't depend on which is the response and which is the explanatory either. So we have a numerical value, depends on these units to measure them. It doesn't tell us whether the association is strong or weak. Two variables must be identified as response or explanatory variables. And the regression equation can be used to predict values of the response variable for given values of the explanatory variable. That is for the slope. R squared, the squared correlation, remember R was the correlation, is the percent of variability in the response variable that can be explained by the linear relationship between the x and the y. Let me give you a better example than you see here. Suppose you look at apartments for rent. As the square footage goes up, the rent on an apartment typically goes up. But it doesn't only depend upon the square footage. It can depend upon the neighborhood, whether or not it comes equipped with a refrigerator and stove, all sorts of things. So what part of it can be interpreted to be explained by the square footage? Well, that might be the R squared. Okay, so that might be the variability. So if we look at one, and we're going to look at one right here, say it was 37.7% was explained by the square footage. The rest is explained by something else. So here they're using the Facebook versus the internet. And that ends that section for us.